You know, we always talk about processor speed in terms of gigahertz, but have you ever stopped to wonder what's really going on inside that little chip that powers, well, everything? How do they actually engineer these things to be so ridiculously fast? Well, today we're going to peel back the layers and get right into the core philosophies that make it all possible. Let's get into it.
It might sound crazy, but literally everything your computer does, from playing a 4K video to just moving your mouse, it all boils down to a super simple and just relentless loop. The processor, at its heart, is just doing the same basic thing over and over and over again.
And that loop is just three simple steps: fetch, decode, and execute. It grabs a command from memory, figures out what that command is telling it to do, and then it does it. That's it. That is the fundamental heartbeat of all computing. But the real genius and the big debate is in how you design those instructions in the first place. Yeah, that simple little loop led to this huge fork in the road for processor design. It created two totally opposite philosophies about the best way to get work done. You can think of it like this. Is it better to have a few really powerful complex tools or a whole bunch of simple specialized ones?
So, in one corner, you have CISC. That stands for Complex Instruction Set Computing. And the whole idea here is to make each instruction a powerhouse. You want to accomplish a big, beefy task with just one single command.
So, for example, look at a multiplication command in CISC. This one instruction is incredibly smart. It doesn't just do the math. It also knows how to go out to memory, grab the two numbers it needs, and then, after it multiplies them, it knows how to store the result back in memory. All of that is packed into one single, complex instruction.
And in the other corner, you have RISC, Reduced Instruction Set Computing, and this philosophy is the polar opposite. It basically says, forget these big, complicated instructions. Let's make every single instruction as simple, small, and fast as humanly possible. The whole game is to break down every big job into a bunch of tiny, easy steps.
So to do that exact same multiplication, a RISC processor has a totally different approach. It takes four separate instructions. First, it has two simple load commands to pull the numbers from memory into these little super fast storage spots on the chip called registers. Then, a multiply instruction works only on the data that's right there in those registers. And finally, a store instruction puts the result back into memory. Each step is dead simple.
So if we put them side by side, you can really see the trade-offs. CISC uses fewer but more powerful instructions, but each one can take a different amount of time to finish. It puts more of the work on the hardware. RISC uses way more instructions, but each one is simple and, ideally, takes just one tick of the clock. It puts more of the work on the software. And you see this play out in the real world, right? Your big, powerful desktop CPUs are often based on CISC, while pretty much every phone and tablet runs on an efficient RISC-based chip.
Okay, so RISC sounds pretty great, doesn't it? Every instruction takes just one clock cycle. It's simple, it's fast, it's predictable, but, and this is a big but, this single cycle idea hides a massive problem. Here's the catch. Even in a simple RISC design, not all simple instructions take the same amount of physical time. Talking to memory, for instance, is just naturally slower than adding two numbers that are already on the chip. But since the whole processor marches to the beat of one clock, you have to set the speed of that clock to be slow enough for the absolute slowest instruction to finish. This means that for every faster operation, the processor is just sitting there, twiddling its thumbs, wasting time.
So how do you solve this huge efficiency problem? Well, engineers came up with an absolutely brilliant solution, and they stole the idea from something we're all familiar with, the factory assembly line.
The solution is called instruction pipelining. The big idea is this. Instead of trying to do that whole fetch, decode, execute process for one instruction all at once, you break it down into smaller, separate stages. And here's the key. Each stage can be working on a different instruction at the exact same time. So a classic RISC pipeline, for instance, breaks the job into 5 stations on the assembly line. First, you fetch the instruction. Then you decode it. Then you execute the math. After that, you might need to access memory. And finally, you write the result back. 5 distinct steps.
So let's watch this happen. On the very first clock cycle, instruction 1 enters the first stage, instruction fetch. The rest of the assembly line is empty, just waiting.
Now, let's jump ahead to the third clock cycle. Look at that. The assembly line is already getting busy. We have 3 different instructions being worked on at the exact same time, each at a different station. Instruction 1 is being executed, while 2 newer instructions are right behind it in the pipeline. And by the 5th clock cycle, this is where the magic really happens.
The pipeline is now completely full. Every single station is active, working on a different instruction. This is peak efficiency. And right at the end of this cycle, instruction 1, the one that started it all, finally finishes and comes off the assembly line.
See, that's the whole secret. You're not actually making any single instruction go faster. It still takes 5 clock cycles for one instruction to get from start to finish. But by overlapping them, the entire factory is now churning out a finished product at a much, much faster rate.
So what's the ultimate goal of all this complex choreography? What is the magic number for processor efficiency?
It's 1. The holy grail is an effective throughput of 1 instruction completed per clock cycle. So even though each one takes 5 cycles to travel the whole pipeline, once it's full, a brand new, fully completed instruction pops out the end on every single clock tick. That is the secret sauce behind modern processor performance. Of course, this is all in a perfect world, an ideal scenario. But what happens when things aren't so perfect? What if an instruction down the line needs a result from an instruction that isn't even finished yet? What happens when the assembly line gets jammed? Well, that's when things get even more interesting. And that's a story for another day.